session, late morning session. We're going to continue the CARS symposium with next speakers. It is my distinguished honor to introduce Dr. Yanxiao Zhao. The next talk is actually use of intelligent reflecting surfaces for and against wireless communication security. Dr. Zhao is currently an associate professor in the Electrical and Computer Engineering Department at Virginia Commonwealth University. Dr. Zhao's research interests include, but not limited to, Internet of Things, 5 and 6G communications, cybersecurity, wireless networks, including cognitive radio networks, vehicular networks, and wireless autonomous networks, and wireless body area networks, software-defined networks, device-to-device communications, wireless energy harvesting, power management, and communications in smart grid. That's a mouthful. There's a lot of areas that her expertise is well known. Dr. Zhao's research has been supported by NSF, NASA, and Air Force. Dr. Zhao has published over 70 papers in prestigious journals and international conferences. She was the recipient of Best Paper Award for 3 international conferences, WASA 2009, China Com 2016, and ICMIC 2019. She has been actively organizing international conferences by serving as TPC chairs, publicity chairs, and TPC members. She is an IEEE senior member. With this, it is my pleasure and distinguished honor to introduce Dr. Zhao. Dr. Zhao, could you please share your screen?
Sure. Thank you, Dr. Prakash. Thank you for the very nice introduction. I'll share my screen.
Yes, let's see. I think we can see you, but I think... Yes, we can see. Yes, we can see your screen. Yeah.
Okay, I'll go to the slideshow.
Were you able to hit slideshow?
So now looks good?
Yes, it's good. Go ahead. Yeah.
Okay. All right. Good morning, everyone. My name is Yanxiao Zhao. Today is my great pleasure to give a talk about intelligent reflecting surface for and against wireless security. Since Dr. Prakash already introduced my bio information, so I'll skip this one. Today, this is the outline of my talk. In the very beginning, I'll briefly talk about 6G and beyond applications, requirements, and some enabling technology. Then I will talk about the main character for today's talk. That's the intelligent reflecting surface, IRS. I'll talk about IRS-related research from 3 perspectives. The first one, I'll introduce the security and the threats in IRS-assisted wireless communication. Then I also talk about angle arrival estimation integrated with IRS system. The last topic I'll talk about is about machine learning powered IRS model and the vulnerability to adversarial attack. At the end, I'll draw some conclusions. So we all know that nowadays we have seen the rapid growth applications of wireless communication networking, including almost in virtually every sector in our daily life, right? Including real-time surveillance, smart city, transportation, intelligent transportation. And nowadays, we also see more and more exciting and new applications. For example, we all know that the extended reality is getting popular, right? Like virtual reality, augmented reality, and also some other interesting applications, 6G driving applications, something like the brain-computer interaction, blockchain, and the divided technologies, right? And we believe, right, more and more new application will be emerging in near future. And we also agree 6G is not just a mere exploration of more spectrum at high frequency band, right? We believe the 6G will be the integration of upcoming technologies driven by new demands. Some major drivers here for 6G we see a lot, right? High speed, spectrum, and energy efficiency, and also some integration of communication, sensing, control, and computing, right? And some we know to meet these new demands and the new applications, so we also need to design some enabling technologies. So here I just list some of them. For example, the edge AI, the mobile millimeter wave and the terahertz communications, and also communication with large intelligent surface. So in today's class, in today's talk, I'll mainly focus on this part, the intelligent surface here. So in recent years, IRS has received a lot of attention from the research community because it provides great flexibility to reprogram the wireless environment. So here we see, right, this IRS, you know, here we can deploy, for example, we can place IRS on the wall, right, either inside or outdoor. So for each element, those are passive materials. They can reflect signals. So that what's the benefit from this one? So let's look at one scenario here. If we have blocking obstacle, right, between the transmitter and the receiver, means there's no line outside communication, so that they cannot communicate successfully, right? But if we have IRS here, and they can, for those reflecting elements, they can reflect the signal. So somehow they can bypass the obstacle and to reach the receiver successfully. So we can see the power and the flexibility of IRS. So that's why many researchers, they are working on this area. So the benefit of IRS, including the low cost, those passive materials, they are low cost, and also energy saving. Also, there's no interference from each elements. So that's why they are getting popular, and we treat this as a promising technology for the next generation applications. And also what we can do, since they can reprogram the wireless environment, right? What we can do, for example, we can adjust, we can control the phase shift of each element, so that we can make the signal, we can make the reflected signal either constructively to the receiver or destructively to the receiver. So this gives us flexibility to control the wireless environment. And here, let's look at this simple scenario here. We have transmitter, we have receiver here. We have this is the receiver. And for this, for each element, for example, here, if we assume they have n reflecting elements, right? For each element, they will reflect the signal. So that's why in total, they will have n reflected path. And this one is a direct path, right? The line outside. So together, we are able to derive what's the received signal RT at the receiver side. And further, we are able to derive what's the signal to noise ratio at the receiver side. We consider all these n reflected paths plus along with the direct path, we derive the signal to noise ratio. Further, in applications, what we can do, we can change as an R by control the phi, that's the phase shift from each reflecting element. Okay, this slide, we summarize some potential applications of IRS. Here, the first application, let's look at the user at dead zone. So here, when we say dead zone, means there's no direct communication between transmitter and the receiver, so that we can use the IRS to reflect the signal, right? So that the receiver is able to receive the signal successfully. This is important. This application is important for the millimeter wave communication, since we know this type of communication, they are very vulnerable to the blockage. The second scenario, now let's look at this one. So we have eavesdropper here. If the eavesdropper is very close to the transmitter, so the eavesdropper may be able to overhear the message, right? So we can also use the ARS to mitigate the signal received by the eavesdropper so that the eavesdropper cannot hear the signal successfully. The third application, that's the user at the call edge. So now look at this scenario. This is intended transmitter, but since the user is very far from the intended transmitter, and at the same time the user is closer to a neighboring base station, so this base station may generate interference to the user, right? So in this scenario, what we can do, we can control the ARS to strengthen the signal from the intended transmitter. At the same time, we can also reduce the interference from the neighboring base station. The last scenario, the last application, we can also use ARS to the massive device-to-device communication. So for example, here, we can use we may select different components, different elements to perform reflecting to different D2D pair. So in this way, those D2D communication can occur simultaneously. So those here, we summarize some potential application of ARS. And due to just now, I already mentioned some benefits of ARS, right? Since the low cost, energy saving, flexibility, and reprogramming the wireless environment. So we believe in the future, in near future, wireless network will see the ARS deployment. For example, we may place a small ARS in the meeting room, in the office, and we may also deploy the ARS from the outdoor walls over the buildings so that we can improve the communication quality. So just now we mentioned many good things about ARS. On one hand, we know we can leverage ARS to improve the communication quality. On the other hand, we also need to be aware if the ARS is too controlled by malicious attackers, right? They can also launch some malicious behaviors. So for the next slides, I'll quickly summarize some scenarios again from the security and also from the threats part. The first scenario A here. So we will present this scenario from how to secure the communication. So in this scenario here, so we have a base station. This is the legitimate transmitter. We have a legitimate user receiver here, and there's an eavesdropper, right? So here we try to prevent eavesdropper to overhear the signal here. And then what to do? One way we can do, for example, we can use a very low power at the base station side. So the eavesdropper cannot hear the signal. At the same time, what we can do, we can control the ARS to strengthen the signal from base station to the receiver. So by this control, we can see the SNR between legitimate base station and the receiver will be significantly increased. And also the SNR between the base station to the eavesdropper is sufficiently low so that the eavesdropper cannot overhear the signal. So this is one scenario. The next scenario, so we can also use ARS to mitigate attack from a legitimate transmitter. So here, give you a scenario here. So if there's a malicious attacker here at this position, and we have a legitimate user, so the attacker try to send message to user. What we can do, we can control the ARS. We can control the ARS to mitigate the signal from malicious attacker so that a user will not be attacked. The next scenario we'll talk about. So in scenario A and B, we talk about this from how to secure the communication perspective. As I mentioned just now, right, it's also possible attacker may take advantage of IRS and do some bad things, right? So here now let's look at the scenario C. We have base station here. This is the legitimate payer. This is the legitimate payer, right? So we have a eavesdropper here. So eavesdropper can also take a control IRS so that to make the signal from base station to itself stronger. In that way, so the eavesdropper is able to overhear the message. So the result, we know in this scenario, right, the scenario between the SNR between base station and the eavesdropper is increased so that the eavesdropper can steal some information. The next scenario, so for example, we have attacker and attacker control the IRS so that the attacker can interfere communication between the legitimate payer or transmitter and the receiver. So just now we present 4 scenarios. From all these scenarios, we can see what we do. So we can use IRS to control SNR, right, signal to noise ratio, further to either strengthen the signal or to weaken the signal. So we have done some simulations, use a simulator. So here, this figure we show, so the TX, that's the transmitter. Just now we summarized 4 scenarios, but we can see for all these scenarios, we control SNR. So either increase SNR or either reduce SNR, right? So when we run simulations, we mainly focus on the SNR increment and decrement. For example, for scenario A and C, we just presented, right? So we try to improve SNR, either improve SNR for the attacker or either improve SNR for the legitimate user. So so here, this figure, that's the position. We set this is the TX, and this one is the receiver. And we also try to observe what's the impact of the position of ARS. So that's why we deploy the ARS at 2 different positions. This is the one position, and this is another possible positions. Then we run simulations. We observe what the SNR changes along with the transmission power. So now look at this figure. Look at this one. This at position 1. So here we observe SNR without ARS. So that's this one. The last one, this is the without no ARS here. And also we try to deploy the SRS with different elements, 16, 64, 256. Then we observe, we calculate SNR value. So this one is no ARS. The next one that's with N equals 16. This one equals the element number, that's the 64. This one, that's the 256. Now we can observe, right? By controlling the phase shift. So we need to design what's the appropriate value of phase shift so that we can further control the SNR. The SNR increases along with the power. At the same time, we can also observe with a larger number of elements, reflecting elements, we can see SNR increases. So we conducted simulation at 2 positions, at these 2 positions, and we observe the similar trends here. So there's another position we can observe the similar trends. The second part, when we perform simulation, similarly, we also put the ARS at 2 different positions. Then we try to control the phase shift so that we can decrease the SNR. So here, that's the deployment of transmitter receiver to ARS. And now let's look at the simulation result. So no ARS, the top one, the top plot, that's for no ARS, was the SNR. Then we also run simulation for different element numbers, similar to the previous one. So we have 16, 64, 256. And now we can see if we control the phase shift appropriately, we can decrease SNR. And also we see if we have a larger number of reflecting elements, the SNR will be decreased, will be decreased more. So this the simulation results. When we run simulation results, we mainly focus on the SNR increment and decrement. For this research, we know there are some challenges. What are the challenges? So when we present the scenario, we know, okay, so the ARS should know which signal is malicious signal, which signal is legitimate signal, right? Which one is a good one, which one is a bad one, so that the IRS can further do some corresponding actions, right? For example, if there's the intended signal, the IRS would like to strengthen that one, right? If the signal is malicious one, the IRS would like to mitigate that one, right? To weaken that signal. So here the challenge, so the IRS should have the ability to identify which signal is malicious or not, right? In the existing research, they just assume IRS know this. So here we propose a solution and try to see, is that possible IRS itself can determine the signal is malicious or not. So for example, here, if the receiver receives multiple signals from different sources, how does the IRS know, okay, the signal is malicious or not? So we propose to use the angle of arrival algorithm with IRS. The main idea like this. So for the traditional ARS, all elements are passive. But what about if we have a hybrid architecture? For the hybrid architecture means, okay, for those elements, the dominating parts are passive, but we do have some active elements. So if we have active elements, we may use this as a smart antenna. We can use this as an antenna array so that we can further apply the angle of arrival algorithm for the ARS system. So we propose this idea, and we use a hybrid ARS architecture. So we have dominant passive elements with a small number of active sensing elements. For the number of active sensing elements, don't need to be large. For example, could it be 2, could it be 4, could it be 8? For those active sensing elements, they work on 2 different modes. The spectrum sensing mode, another one is the reflecting mode. So when they work on the sensing mode, we can use this. We can make this serve as antenna array. So here, let's look at this part. For the AOA, we just use the traditional music algorithm to run simulations. So here, for example, if we assume it has D sources from different users, one user is the legitimate one and others are unknown one. So the equation 1 represents the signals from all these D different sources at time t. So further, we can represent the signal since we consider D sources. So for each active element is able to receive all these D signals along with noise. This is the noise along with noise. So that's the received signal XIT at the active element I. Further, we use the matrix representation to represent the the received signal. Then we calculate with the correlation matrix from the eigenvalue decomposition. So we can rewrite this as a orthogonal signal and a noise space. For the music spectrum, spatial spectrum, this is the formula. As we can see, right? If the angle is from if this part, so we can observe if the signal is from the known angle, we know the spectrum will have a peak. Whenever this means, whenever if we observe a peak from the spectrum, we can estimate, right, what's the incoming signal. So here, if we try to use the AOA algorithm, we also need to have an assumption here. We assume the receiver knows the angle of the incoming legitimate transmitter. So once we know this, we observe what's the estimate angle with the intended angle. Observe what's the difference. If their difference is small enough, we just assume the signal is from the legitimate one. Otherwise, we assume the signal is from the malicious one. Okay. So we run some simulations. For example, we consider different number of active reflecting elements. Here we consider 5, 10, 15. Then we also assume there are 4 incoming signals at different angles, at different degrees. Here we use -20, -10, 10, 20 as example to show this 4 different signal sources. Then we observe the performance of music, and we see with higher, larger number of active sensing elements, we can see the performance, the resolution is higher. Since these angles are different with each other a lot, so the music works pretty well. Then we also try to observe what's the resolution, what's the accuracy of AOA. We know if the signal sources are very different from the angles, music works pretty well. So what about if they are very close to each other? What's the result? So now let's take a look at this. So we make the angle are different. So here, the red one, right? The red plot, this one, we see the angle is at 1, 2, 3, 4, 1 degree difference. The music works well, right? Then we try to make the angles are close, degrees are close to each other. So the black one, we make the angle just 0.5 degree, and we see, okay, it's also fine. Then if we further make those sources are very close from the angle perspective, and we see, for example, the blue one, right? The difference just like a 0.25 degree, the music is not able to distinguish one from another one. So here we also see the limit of music algorithm, right? If the angles are very close to each other, music probably doesn't work. And also another thing, if the malicious user is at the same angle with the legitimate user, the music may not work as well, may not work either. Those are limits about this approach. So we are working on new solutions, try to improve the music algorithm. Okay, I see one question on slide 19. How many active numbers were used? Which one? 19. Let me see. Oh, this one. Okay, see, for this one. Oh, we didn't write down. Let me see. For the previous one, we try a different elements number like 5, 10, 15. For this one, I need to double check. For this one, for either 5, 10, 15, they have the similar trend. So that's why we just present one result here. For 5, 10, 15, they will follow the similar trend. Okay, thank you. Okay, so just now we talk about the how to use the music AOA integrate with IRS so that IRS is able to distinguish malicious signal from legitimate one. Okay, another challenge we also know due to the large number of reflecting surface. So it's very difficult to model the channel to know, okay, to derive the channel vector for all the reflecting surface. Since we know eventually, right, we would like to, for example, we would like to control IRS, we would like to control the phase shift of IRS so that we can improve the SNR. Eventually, we are able to improve the transmission rate. So here we consider this challenge and try to see how to derive the optimal phase shift so that we are able to achieve optimal transmission rate. So here, in current research, they use different methods. We try to explore using the machine learning method and try to see this works or not. Okay, so try to apply a machine learning method to the IRS. So once again, we need to consider the hybrid architecture. So for the hybrid architecture means for the IRS, it has passive reflecting elements. Also, it has some active one. Once again, here, the active one, the number of active elements doesn't need to be large. Could be 4, could be 8, that's fine. Then, so here we have transmitter, we have receiver here. And we can call the position of, IRS all the number of active elements as the environment descriptor. Then we make this as an input to a machine learning model. The output will be the optimal phase shift matrix. Further, actually, if once we get the optimal phase shift matrix, right? So that's the phi, we can control as an R, eventually we can control the transmission rate. So once we know the optimal phase shift, eventually we can get what's the achievable transmission rate here. Okay. So we design feed-forward neural network. So it has 4 layers. The input, that's the environment descriptor, and the output, that's the optimal phase shift. Could be also that's the achievable transmission rate. So it has 4 layers, and for each layer, we can see how many neurons here. We use 2M, 4M, 4M. So the M indicates what's the number of reflecting elements. And we run some simulations. We use an online available data set. So we use the ray tracing scenario. So for this one, we can see it has a transmitter. It has a fixed transmitter. And also it has a receiver area. So we can see, okay, this is the receiver area. It's a big one, so it's an XY grid. And how many possible locations? So over 5,400 candidates. Those are possible locations of the receiver. Then here, that's the IRS deployment. Okay, so we use this data set and run simulations. We compare the result here, the right hand figure, that's the simulation result. The left figure, that's our simulation with scenario. So based on this scenario, we run simulation and we observe what's the achievable rate. So here we consider different number of elements. We consider the blue one, that's the 32. That's the 32 times 32. And the red one, that's the 64 times 64. So we run simulation and see this, the horizontal one, that's the possible optimal transmission rate. We can see we can achieve it if we have a larger data set size. And for both situations with different number of elements, so the result looks fine. They approaches the optimal transmission rate. Okay, after developing this model, so just now we present the machine learning based model. After developing this one, then we also work with our collaborators. So they will implement adversarial attack on this machine learning based IRS model. Okay. Okay. So the simulation platform. Okay, so for the first one, there's an online simulator. We use the online simulator. For the second one, okay, let me see. Okay, let me answer the question later. Okay, so we also work with our collaborator. They implement adversarial attack on the machine learning based IRS model. So the adversarial attacks we consider 4 different attacks: FGSM, that's a fast gradient sign method, the basic iterative method, and the BM and the PDD. We try to evaluate what's the vulnerability of the machine learning based IRS model. So then, let me see. Then we evaluate the vulnerability. The left figure, those undefined one, those show the result of undefined one. So we observe what's the mean square error for different type of adversarial attack. We see pretty bad for this one, pretty bad. Then our collaborators, they also propose a defensive method, try to mitigate the impact of adversarial attack. So they use the defensive distillation method, try to improve the resilience of the machine learning based model. So if you would like to learn more, I believe I list the paper. Oh, I thought I list the paper. Yeah, we published one paper on the IEEE access. So later you may also read the paper if you like to learn more details. Okay, so now let's quickly go to the conclusions about today's talk. So today I present 3 topics. The first topic, we look at the security and threats using IRS. So we try to study the potential security impact of IRS on wireless communication systems, and we propose different scenarios and analyze the SNR, run simulations, try to evaluate the IRS system from the perspective of SNR increment and decrement. And then we also consider the potential integrating AOA estimation for signal classification for the IRS system. We use the music as an example to show the performance, and we also learn some limits from music algorithm. So currently we are working on how to further improve the AOA algorithm. For example, what about if the signals they are from the same angle? Then what to do? Maybe we can apply some machine learning methods to do that, to further improve the accuracy of AOA. And also we explore the machine learning based IRS model and try to see what's the vulnerability of the machine learning based model. We did some adversarial attack and see those models actually are vulnerable under adversarial attack. So in future, we can also need to see how to improve the robustness and the resilience of the model. Okay, all right. Thank you. This is my email.
Thank you, Dr. Yan. I think that was a great presentation. I think appreciate for sharing your work on hybrid IRS architecture. It's very interesting work. And how's your how do you handle interference? Do you look at other angle of other parameters other than angle of arrival when we look at these four scenarios? Also looking at a scalable architecture where the M is so large, and I know that you had some insight on distinguishing interference versus the attack scenarios versus the legitimate signal. But I wonder, how do you think we should handle the interference? Or how are you seeing that?
Okay, so do you mean the when you say the interference, do you mean the interference from each element or from the environment?
It could be both, right? It could be a combination of what.
Okay, yeah. For the environment, so since there's a preliminary work, we just look at the simple scenario. For example, we just look at one transmitter or one receiver. For the interference, right now, if many users get involved, we know the communication situation will get worse, right? So that part for the interference, we didn't study that much in the IRS scenario. For the element reflecting element one, so they normally assume those are passive. Those are passive reflecting element. They just ignore the interference for now.
Great. And I have one question from an audience. Does an attacker need physical access to control or manipulate the IRS surface?
Does the attacker need physical access to control? Oh, I see the problem. Okay, I think the audience question, like I just present, right? So what about if IRS is controlled by attacker? Is that the question?
I'm assuming that's right. Yeah.
Yeah. Then I think, see, the IRS, the attacker, they can also deploy IRS, right?
Correct.
Yeah. So the attacker, they can deploy their own IRS, right?
Yes.
Okay, so that's why we see the potential risk. So what about if the attacker, they can deploy their own one? And we know, right, if the attacker is controlled by if IRS is controlled by good users, right, we may have many benefits, but it's possible the IRS can be also controlled by attacker.
Great. Thank you so much, Dr. Ann. I appreciate your time. In the interest of time, we're going to stop the questions for this session. And again, let's thank the speaker. We're going to send you a nice plaque that we have. So we'll be in touch with you to send this plaque. Thank you, Dr. Ann, for your time.
Okay, thank you. Please feel free to send me email if you have any question. Okay, thanks.